ATP per pass electron transport chain. Okay, so we're at pyruvate, we're done with glycolysis, but because we're working aerobically, instead of going to lactic acid, we're going to go to acetyl-CoA. This reaction also produces hydrogen. Has to be picked up by the NAD. There's enough hydrogen here to fill 2 more NADs. Okay, so here again, we're going to get 2 NADs, which is going to become 2 NADHs. Electron transport chain, 2 passes, 2.5 ATP each, for a total of another 5 ATP. Okay, then we get to acetyl-CoA, and we enter the Krebs cycle. The Krebs cycle is, again, a series of reactions just like glycolysis. I'm not going to teach them to you. I'm not going to ask you about them. When you get into 446, depending who you have, you might need to memorize all the reactions in Krebs. But for me, you need to know the ATP, and you need to know 3 of the enzymes. So I'm going to do the ATP on this one. I'm going to do the enzymes on this one. Okay, so Krebs is always drawn in this direction, clockwise. So anything I put up here is happening at the beginning of Krebs, middle of Krebs, end of Krebs. So I'm going to put the things that I'm putting on generally where they're happening in the sequence. For this class, I'm not going to grade you on where on the circle you put them. I'm going to grade you on spelling. But I'm not going to grade you on where on the circle you put them. But for those of you who will be going on to 446, if you end up having to memorize all the reactions in Krebs, it might help you to know where they go. So you'll have those pieces to put in already. Okay, so I'm going to put them in the right place. When you draw it back from me, I don't care where you put them. Okay, so in the beginning of Krebs, we have a reaction that's creating more hydrogen. It's going to be picked up by NAD. There's enough hydrogen in these reactions to fill 3 NADs. I'm just going to put NADH. Electron transport chain. How many ATP each?
2.5.
For a total of how many ATP here? 7.5 ATP. Everybody okay with that? Okay, we keep going through reactions. When we get down here, there's 1 ATP that's produced right here within the Krebs cycle. It can be called a direct ATP, it can be called a substrate level ATP. It's being produced right here within the Krebs cycle, not from the electron transport chain like all the others. When we get up here, we have more hydrogen being produced. But these hydrogens, instead of calling an Uber, they're going to call a Lyft. So they're going to take a different electron carrier. This one is called FAD. And then when it picks up the hydrogen electron, it'll be FADH2. So Lyft is a little bit cheaper. So it doesn't give you quite the same service. So instead of dropping you off right at the front of your party, it's going to drop you off around the corner from your party. So you have a little ways to walk. Okay? Which just means instead of handing off its hydrogen to the first cytochrome, it's going to hand off its hydrogen to the second cytochrome. The importance of that is that it's going to get fewer redox reactions. And if it gets fewer redox reactions, it's going to produce less energy, and therefore less ATP. So 1 pass through the electron transport chain, if it's initiated by FADH, gives you 1.5 ATP instead of 2. And there's only 1 FAD here. Okay? You don't need to know why you get fewer ATP from the FAD. Again, that's 446 level. You just need to know that if it's initiated by FAD, you get 1.5. If it's initiated by NAD, you get 2.5. So we can do the math. Okay? So, how many total ATP from 1 Krebs cycle?
10.
The exact same thing is happening in Krebs cycle 2. You do not need to write all of that again. We're going to have an agreement that they're equal, they're identical. Okay, so I'm just gonna put another 10 ATP here. Okay, so now we need to count up the ATP. If we start from 1 molecule of glucose, we come into the muscle as G6P, we go through glycolysis, and then we go to acetyl-CoA through both Krebs cycles and a bunch of electron transport chains. We're going to count up those ATP. Let's do it together. Going from glucose to G6P, what's happening with our ATP? Okay, from G6P to 2-pyruvate, what's happening? -1 plus 4. We're also getting the +5 from the 2 NADs. Okay, that's happening in between glucose 6-phosphate and pyruvate. This reaction is going to create those hydrogens. It's going to send us off to the electron transport chain. Then, between pyruvate and acetyl-CoA, what's happening with our ATP? Plus another 5 from those 2 NADs. Krebs cycle number 1. Krebs cycle number 2. How many ATP from Krebs cycle number 1? How many ATP from Krebs cycle number 2? Okay, do that math. Is it 33 or 32? 32 ATP. That's a number you need to know. This is the complete oxidation of 1 molecule of glucose. Complete oxidation means we're going through the aerobic metabolism, completely metabolizing the carbohydrate using the aerobic system. Okay, so the complete oxidation of 1 molecule of glucose yields 32 ATP. What if we came from muscle glycogen? What would be different on here? We wouldn't lose this first one, so we'd end up with 33 ATP if we came from muscle glycogen. What if we came from liver glycogen? 32. Those are numbers you need to know. What was our maximum ATP from the anaerobic metabolism of the carbohydrate?
3.
Our maximum was 3 if we were coming from muscle glycogen. Now we're at 32 and 33, significantly more when we incorporate the aerobic metabolism. But it requires oxygen, so it's slower. Do you have questions for me? I'm going to add some enzymes. Okay. So, from pyruvate to acetyl-CoA, your enzyme is pyruvate dehydrogenase. In the Krebs cycle, I'm only going to write the enzymes on the Krebs cycle down here. They are also on this Krebs cycle. But you don't need to write everything twice. I usually write the ATP on one and the enzymes on the other. Just keep them separate and we have an agreement that they're identical. Okay, so beginning of Krebs cycle, you will have citrate synthase. Later on, is this blocking you guys? Isocitrate dehydrogenase. And then succinate dehydrogenase. Okay, again, with those enzymes, I won't grade you on where on the circle you put them, but that's generally where they occur for later in 446. Of these enzymes, isocitrate dehydrogenase is the rate-limiting enzyme. What does it mean to be the rate-limiting enzyme?
Control the speed of
It
the
controls the speed. So if we want this process to speed up, we activate that enzyme. If we want this process to slow down, we inhibit the enzyme. Enzyme for the redox reactions will be cytochrome oxidase. Rate limiting, and PFK is the rate limiting enzyme for glycolysis. It's my masterpiece. You guys need to be able to draw this.
just like all of it,
The whole thing.
everything.
All the fates of lactic acid, all the enzymes, all the electron carriers, all the ATP. I'll leave it up there so you can get up closer and take a picture of it. I realize it's overwhelming, but there's a 99.9% chance this drawing will be on your midterm. I always leave that 0.1 because there has been one time in the decades that I've been teaching that that page got left off the exam at the copiers. So I always have to account for that. But I'm planning to put it on your exam. It's a 35-point question, which is a lot. It's about a 150-point exam. It's a lot. But think of it this way. If I told you you could get 35 points on your midterm by memorizing all the lyrics to Eminem's Rap God, could you do it? Yes, you could. Yes, you could. That's probably harder than this, actually. So if I tell you you can get 35 points on your midterm by drawing this, you can do it. I'm going to tell you exactly how to do it.
Is there partial credit on that?
Absolutely. So here's how you do it. Put a stack of blank paper on your kitchen table. Minimum 3 times a day, you're drawing this out from memory. Okay? Staring at it already drawn in your notes is not going to prepare you for a blank paper on your test. Okay? 3 times a day, minimum, you're drawing this from memory to the best of your ability to fill it in from your notes. You guys have 2 weeks until your exam. So if you're drawing this minimum 3 times a day for 2 weeks, you will be able to draw this by the time your exam comes. You just have to decide you're going to do it. Go ahead.
This is just to kind of help myself out. How many actual enzymes are there on this chart, and then how many actual technical authors and listeners do we have to write down? Because I was counting it right now. There's 14 enzymes, I believe, that we need to know exactly, and then.
So I'm not going to ask for the genesis, and I'm not going to ask for the glucosalanine cycle. But this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 enzymes. Did I count this one?
No.
11, and I'm not going to do the genesis. So I counted 11 enzymes. I will tell you that historically, 95% of my students get between 30 and 35 points on this. You don't have any problem memorizing it. What they miss points on is spelling. But most of my students have this down by midterm time. In fact, most of my students are begging me to put this on the final because it's easy points. Am I right, Savon?
Yeah.
You can do this. You just have to decide you're going to do it and put in the time. I will tell you also the details of the electron transport chain with the redox reactions will be a separate question. So when you draw this, you can literally just put a box that says electron transport chain and the enzyme cytochrome oxidase. You don't have to give me any details on that. I will ask you that separately though. Okay, and you have to show that the electron carriers are going to the electron transport chain. That's it.
We need to show how much ATP is per NAD.
Yeah, you'll need to show that here when you're counting the ATP. So you also need to show me how the numbers add up, like this.
Is the abbreviation fine if we have it listed on the total drawing?
Yes. So when you're adding up the numbers for me, I don't need this explanation of where they are, because I'll be able to see that on your drawing. So you can literally just put the -1, -1, +4, +5. But the numbers that are here need to be on here. So common mistake is to confuse these two NADs with these two NADs and maybe leave these off. So if you have -1, -1, +4, +5, +5, because you've memorized this, but these NADs aren't here, I'm going to say those numbers don't match these numbers. Then you're going to lose a point. Okay, so make sure you have everything on there and show me that it adds up to the number that you want it to add up to.
Do we have to also explain why it's 33? Or do you
No.
just want 32?
It depends if I'm asking you for glucose or glycogen.
And for the liver, we need the amino acids and Cori cycle with the.
I won't want the amino acid Cori cycle, I'll want the lactic acid Cori cycle and the glycogenolysis. What else do you want to ask me?
Can we abbreviate glucose 6-phosphate?
Nope. You can abbreviate NAD, you can abbreviate ATP, ADP, phosphate, that's about it. Yes,
How do you pronounce the last dehydrogenase?
succinate,
Succinate?
succinate dehydrogenase. Okay, I want to talk about this theoretically a little bit more before we take a break. So, pyruvate can either become lactic acid or it can become acetyl-CoA. What do you think determines which direction it goes?
Phosphofructokinase.
Phosphofructokinase is up here. Oxygen.
The amount of ATP, the amount of AMP.
So let me ask you this. Which direction do you think your body would prefer the pyruvate go? To acetyl-CoA, because we can get a lot more ATP that way. So that way is aerobic, right? So at low intensity, your body's working aerobically. So at low intensity, most of the pyruvate is becoming acetyl-CoA. Okay? There's always a little bit of lactic acid being produced, because remember, none of our systems ever turn off. But very little is being produced, and we have so many different ways of clearing it, it's not a problem. Okay, so sitting in your chair right now, most of your pyruvate is going to acetyl-CoA. If you get up and start walking around, and then start jogging, and then start running, and you're increasing your exercise intensity, PFK is going to be activated. Because we need this process to speed up. The whole purpose of glycolysis is to produce ATP. So if you're exercising, you're breaking down a lot of ATP, we got to tell PFK to make more. Okay, so PFK gets activated, what happens to the speed of glycolysis?
Increases.
It increases. So glycolysis starts speeding up, which means hydrogen production speeds up. And the mitochondria has a limited capacity. Okay, I like to think of this electron transport chain as the women's bathroom at the Staples Center, and the cytochromes are the stalls. So if you go during the best song, stalls are empty, you just go in and out, no problem. If you go at the end of the concert, everybody's trying to go, stalls are full, and there's a long line, right? So if glycolysis is happening fast, lots of hydrogen is being produced, mitochondria is full, the hydrogens start to back up. We cannot let the hydrogens back up here. There cannot be a line. We have to clear those hydrogens. So if the NADH cannot drop off its hydrogen and electron at the mitochondria, the electron transport chain, it's going to instead hand it off to the pyruvate. Pyruvate can accept an unlimited amount of hydrogen and electrons. if you hand a hydrogen and an electron to a pyruvate, we're reducing it, right? Because we're giving it an electron. When you do reduce pyruvate, it becomes lactate. So that's going to produce lactic acid. So this is why as you increase your exercise intensity, lactic acid production increases, right? At some point, your mitochondria is going to hit its capacity, and the overflow goes here. Does that make sense? This is part of what I wanted you to see on your treadmill assignment, which hopefully you did. If you haven't done it yet, please still do it. I wanted you gradually increasing your intensity, comfortable, 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 and then at some point, you're a little bit uncomfortable. That's the point where you've hit the capacity of your mitochondria, and you're significantly overflowing into lactic acid to the point where you can't clear it fast enough. And that's what I wanted to know, when that happens for you, at what intensity. Does that make sense? Yes?
So does that mean we could improve our ability to intensity by
Yes.
mitochondria?
Yes. We can improve it through training, which we'll get to after the midterm. Other questions so far? Yes?
So, when does like fatigue come in this? It's like when you go to the anaerobic side, I'm thinking like, okay, you have all the energy, and then when you hit that point, you start getting slower and slower.
Yes.
So is that
So when you're producing the lactic acid faster than you can clear it, the hydrogen that's in the lactic acid is going to cause fatigue. And we're going to get the details of that in chapter 6. Like way more detail than you want. I promise we'll get there. But there's not really anything causing fatigue on this side. Except when you hit the capacity there, we have to overflow to that side. Do you want me to explain that one more time before I add on?
Yes, please.
Okay, so at rest, most of the pyruvate is going to acetyl-CoA. We're working aerobically. If you start gradually increasing your intensity, we're going to activate PFK to tell glycolysis to speed up. So we activate PFK, glycolysis speeds up. This speeds up the production of hydrogen, which overwhelms the mitochondria. Mitochondria is full. So the NADH cannot accumulate here. It has to release its hydrogen and electron. So if it can't release it at the electron transport chain, it's going to hand it off to pyruvate, which is going to create lactic acid. So as your intensity goes up, lactic acid production goes up. When you get to very high intensities, you're producing a ton of lactic acid. You won't be able to maintain that for very long because it's going to cause fatigue. The burning you feel in your muscles. It's going to stop you. Okay, so now I need to tell you what is happening that's activating the PFK. I'm going to give you 3 things that are activating PFK. One thing that's happening to activate PFK is decreased levels of ATP. Why would there be decreasing levels of ATP when you're exercising? We're using it. We're breaking it down during muscle contraction to bring the myosin head back up to 90 degrees. So the higher the intensity of your exercise, the lower the level of ATP is. That's a signal to PFK, speed up, we need you to produce more ATP. Another trigger for PFK activation is high levels of AMP. Where's that coming from?
PCR reaction.
Which reaction?
ADP plus ADP equals ATP plus
Enzyme? So the myokinase reaction creates AMP. Will you agree this is happening when we're exercising at a high intensity, yes? So the presence of AMP, or the accumulation of AMP, is a signal to PFK, we're doing work here, we need you to hurry up and produce more ATP. Activates PFK. Third factor that activates PFK is high levels of glucose 6-phosphate. That's here. Most of the glucose 6-phosphate that we're getting is coming from glucose. Most of our glucose is coming from stored glycogen. That process is glycogenolysis and is controlled by glycogen phosphorylase. Okay, so when you're exercising, we activate glycogen phosphorylase. That speeds up glycogenolysis. So we start breaking down more liver glycogen. That dumps into the blood as glucose. So we now have high levels of glucose that's going to come flooding into the muscle as glucose 6-phosphate. There's a ton of substrate there. That's a signal to PFK. Let's go speed up the process. Okay, so all of these things are occurring with increased exercise intensity. The more intense your exercise, the more intense this situation gets. Okay, this can't think of the word I'm trying to get. Starting with a C. The more intense your exercise get, the more these things are happening. Okay, the more activated PFK gets. If we activate PFK, PFK is the rate-limiting enzyme for glycolysis. So this is going to speed up glycolysis, speed up hydrogen production, overwhelm the mitochondria. Okay, so we call that low mitochondrial availability because it's full. So NADH is going to drop off its hydrogen electron at pyruvate, reducing it into lactate. So lactic acid production increases as exercise intensity increases. Okay? Let's take a break. It's 5:00.